Everybody's here, so we can start again. Everybody. So we have Ingo Blechschmidt, back in Austria, so from the University of Augsburg. Is it correct? Yes.
Yes.
And here we talk about the reifying dynamical algebra. I'm very curious about what it means.
Yes.
Thank you. You can go.
Thank you very much. Thank you very much for the kind invitation. It's a pleasure to speak in this seminar. I really like the Italian mathematical community, and this is building on work by Berardi and Valentini. I presented that for the first time at the University of Padua a couple of weeks ago, and I hope you will like it. I especially hope so because while I'm using algebra as a concrete example, as a running example throughout the talk, the technique I want to present is not restricted to algebra at all. So I'm hoping that some of you will find some use of the general technique presented in this talk also for your current research. A very rough outline will be the following, and then I will give details. You might recall that a question with some history in commutative algebra is whether commutative rings have maximal ideals. And nowadays, the established answer is that every commutative ring has a maximal ideal, with the sole exception of the zero ring. But to construct these maximal ideals, you need the axiom of choice. You need Zorn's lemma. So we don't have it in constructive mathematics. So we don't have it in computational mathematics. And that seems to be the end of the story in some sense. And what this talk will show that this is in fact not the end of the story. In fact, if we change definitions slightly, then we will obtain the result that also constructively, every commutative ring has a maximal ideal. In direct contradiction to what we learn about maximal ideals requiring the axiom of choice. Yeah, so I hope you will like it. Feel free to interrupt me mid-talk. Yeah, don't save your questions till the end. Just ask them as soon as they arise. I'd like to start with a very basic undergraduate theorem, yeah, of linear algebra. Namely, let M be a matrix with more rows than columns over a field. Assume that M is surjective, or more properly, that the linear map induced by M is surjective. Then we have a contradiction. So a matrix which is taller than it is wide, a rectangular matrix looking like a vertical strip, cannot be surjective. Okay, that's a theorem of undergraduate linear algebra. And let me very quickly remind you of the proof. So let's have a look at this matrix, at such a matrix. Let's just do that orally. Have a look at that matrix, and then have a look at all of each of the matrix entries in turn. It might be that all of those are zero. In case that all of these are zero, then we immediately have a contradiction, because the zero matrix will never be surjective. Okay. It could also be that one of those matrix entries happens to be invertible. That's the only other option in a field. Then using elementary row and column transformations, move that specific entry to the left. And then you change that into the unit of the field, 1, and then you kill off all the remaining matrix, which is again surjective, and hence you can continue by induction. Yeah, so that's the undergraduate proof of that undergraduate statement that surjective matrices with more rows than columns are not possible. Okay, and now let's progress to a more involved case, namely, let M be a matrix with more rows than columns, but now over a commutative ring, or commutative ring A with unit. And again, let's assume that M is surjective, that the induced linear map of M is a surjective linear map. Okay, and then we can again ask, yeah, is that possible? Is that not possible? Under which conditions on the ring is that possible? And the more involved theorem is the following. So we cannot state that this never happens, because there is a ring over which this does happen. But there's only one ring over which this happens, namely the trivial zero ring. So then we have 1 equals 0 in A. That's the more general theorem from commutative algebra instead of undergraduate linear algebra. And the proof, the theorem is interesting. First, there is a basic theorem in commutative algebra, but for the purposes of this talk, this theorem is interesting because of its proof. Let me present to you the standard textbook proof of that theorem. This starts out with a proof by contradiction.
Ingo,
Yes.
one moment. Can you bring the mic closer to your mouth? Or
yeah, I can try. Is it better now? Test.
Yeah, I think it's a bit better. Yes.
Okay. Okay. Yeah, okay. Then I'm assuming that it's okay, yeah?
Yeah, it was okay also before. Now it's just a bit better.
Okay, thank you very much. Good. Okay, if 1 is not equal to 0, then A contains a maximal ideal. Let's call that M. As a quick reminder, what is a maximal ideal and what is an ideal? So just comment. The ideals of the ring Z are the following. So you have the unit ideal, which consists of all integers at the top. And you also have the so-called zero ideal, which consists just of the number 0. Okay, and then you have lots of ideals in between. For instance, the ideal of all even integers, yeah, or the ideal of all numbers which are multiples of 3, or of 5, or of 7, and so on. And then you have many more ideals. For instance, let me scroll a little bit. For instance, we have the ideal of all numbers which are multiples of 4. Yeah? And this is contained in that. And here we have that containment relation. And then we have the ideal of all numbers which are multiples of 6. And there we have this containment relation. Yeah, so 6, this ideal is contained in the ideal containing all the even numbers, but it's also contained in that ideal. Okay, you get the picture, and there are many more ideals, and the 0 ideal is contained in all of those. Okay, and what are now the maximal ideals? So the largest ideal would be this ideal, the ideal consisting of all integers. But this ideal, we'd like to exclude that one, because this is an improper ideal. More interesting are the proper ideals, these which do not contain the unit of the ring, these which don't contain everything there is. Yeah? So these are the proper ideals. And the largest ideals among the proper ideals are called the maximal ideals. So these ideals here, these are the maximal ideals. Okay, just to remind you of this definition of commutative algebra. Okay, Yeah, and it's a theorem of commutative algebra that every non-trivial ring contains a maximal idea. The way this is constructed is, it's not constructed at all. Instead, we concoct it by appealing to the Zorn's lemma and simply stating that since the partially ordered set of proper ideals satisfies this chain condition, there must be a maximal element in that partial order. And then that maximal element is called the maximal ideal. Why is that interesting? It's interesting because we can form the quotient. So like with Z mod n, A mod m contains fewer elements than A, namely it contains equivalence classes, and two ring elements of A get identified if the difference is an element of M. And now this the maximal ideal condition translates to the fact that the quotient is appealed. So much nicer than before. And the matrix M is still surjective when considered as a matrix over the quotient. If we make the ring smaller, then it gets even easier for matrices to be surjective. Yeah, and that almost concludes the proof, because now we have reduced to the field situation. Yeah, we now have a matrix over the field A mod M. It still has more rows than columns, and hence we have a contradiction. Hence, contradiction. Okay, and I really like this proof, yeah, because it's a very, very elegant and quite effortless, because we don't try to do a new proof for the general situation. Instead, we simply try to reduce to the situation which we had before concerning the fields. And we do that by quotienting by a maximal idea. So from this point of view, the proof is very nice and very elegant. However, you could also take issue with that proof. I first learned this kind of issue at the FILMAT meeting in Musumeli in 2018, at the meeting of the Italian Network of Philosophy of Mathematics. Namely, the proof here is at odds with the statement of the theorem. Because the statement of the theorem is very concrete. It's stating that a certain equality holds in the ring, namely 1 equals 0, under the assumption that certain other equalities hold. The statement that M is surjective can be expressed as saying, well, there's a preimage for the first canonical basis vector, and for the second, and for the third, and so on. So the statement of the theorem is extremely concrete, very much down to earth. However, the proof is very much abstract. That already, that abstractness already starts in the very beginning, because this is a proof by contradiction. So not computational at all. So we appeal to the transfinite already in the first 2 words of that proof. And then it gets worse, because in order to concoct that maximal ideal, we appeal to Zorn's lemma. So again, to the transfinite. So this proof requires 2 invocations of the transfinite just to obtain this very concrete statement that 1 equals 0. So in this sense, the proof is at odds with the theorem. Let me show you how the proof could also be, if we would like a more concrete proof. And at least let me show you that in the special case, the matrix has 2 rows and just a single column. Okay. So it would work as follows. Sorry. So what does the matrix look like? It's a row with X at the top and Y. Sorry. I want to write that upside down, but I don't have the key on this keyboard. Just a second. Okay. Okay, yeah. X at the top, Y at the bottom. Okay, so that matrix is surjective. So we have U and V in the ring. Let me switch to it here. In the ring, such that U times X, Y equals 1, 0. And that V times X, Y equals 0, 1. Okay. Surjectivity. Yes. Okay. And then we have the following proof that 1 equals 0. Namely, this one. So you can check that this is indeed equal to 1. So you can check that this equality holds, because like most of the terms cancel. And you can also check that it's equal to 0 here at the right, because all those individual bracketed terms are equal to 0. For instance, Vy minus 1 is equal to 0 because V times Y is equal to 1. Yeah? So this proof is extremely concrete, extremely computational. It's without appealing to the transfinite or to any other constructions in commutative algebra, it vividly tells you that 1 equals 0. However, also this proof has an issue, namely it's not memorable at all. Yeah? I did not memorize this equation here. Instead, I copied it from my notes. And I think nobody could be expected to memorize that this computation. So now we have two proofs, and an elegant proof, which is abstract, and a concrete proof, which is hard to memorize and which doesn't really tell you the deeper reason of the state of affairs. Yeah. Okay, and the goal of mathematical logic or categorical logic, to be more precise, is now to explain in which sense, or explain how the previous abstract proof can be turned into this concrete proof. So I'd like this abstract proof to, I'd like to interpret that merely as a code, as a template, as a guiding template for the concrete proof below. And I'd like to regard the maximal ideal appearing in the abstract proof as a very convenient notion, which helped me to structure the proof. But I'd also like to regard that as a convenient fiction, which I could eliminate from my proof. That's the idea. So devise a technique which automatically turns this proof into that proof. Okay, and in fact, there are a couple of techniques already. Peter Schuster and I just contributed one more such technique, and which is of course interconnected with other such. But first, let me to set the stage. Let me present to you the classic, a standard technique for dealing with that situation. And the standard technique is called dynamical algebra. The idea of dynamical algebra is to have a closer look at the abstract proof and see whether we can mine it for additional computational constructive information. The idea is the following. So in a constructive, the classical proof, using the maximal ideal, will at some point ask the question, is X contained in the maximal ideal? Is X contained in the maximal ideal? And then there might be two answers. There might be the answer yes or no. And in the yes case, we will do some computations, and then finally at some point obtain the statement that 1 is also included in the maximal ideal, and that's a contradiction. And in the no branch, it will be similar. We will do some computations, and then at the end, we will also obtain this absurd statement, which is a contradiction. And so in both cases, we have a contradiction, and that is what we wanted to obtain, and hence we are done. So that's the starting point of dynamical algebra. Hope that the classical proof proceeds along these lines, which it very often does. And then the idea of dynamical algebra is to now have a closer look at what we actually, from a computational point, have managed to verify. So we might be in the middle of the proof. Assume that the proof already established that, let's say, A and B are in the maximal ideal, yeah? Okay, then what does this branch here actually tell us? I'd say it told us the following, namely, that the ideal generated by A, B, and X contains 1. Because, yeah, if we manage to deduce that 1 is an element of M, to deduce that, yeah, we only use the knowledge about M already established. And that's that A and B, some elements A and B are included in M. And also, because we are in the yes branch, that also X is included in M.
Are A and B specific elements here, or just generic?
No, some specific elements which just happened to arise in the proof.
Okay.
Yeah? Depending on what the proof looked like. So perhaps there are some matrix elements, yeah, which we had a looked at in turn, or there might be some other elements. I don't know. Depends on the proof.
Okay, thanks.
The point is, the observation that 1 is contained in that ideal is positive information, and we can use that positive information to now switch to the no branch, yeah, because this tells us that in fact it's absurd to assume that X is an element of M. Instead, we have learned. I could have also written that here, that the maximal ideal together X is the unit ideal, yeah? And that is exactly what the yes branch establishes. And if the no branch now establishes that 1 equals M, then actually we have learned something different, namely that 1 is included in the ideal, in the generated just by A and B. Which is again positive information. Information that this specific linear combination that is a specific linear combination of A and B, which results in the unit of the ring. And now we could continue that. So that was just like a small part of the proof. We have been in the middle of the analyzed proof. In fact, the proof had some beginning, which somehow established that A and B are in M, but we can work our way upwards, and then at the end obtain that one is an element of the ideal generated by nothing at all, so that one equals 0. And that's what we have tried to show. So that's the general idea of dynamical algebra. Yeah, reread the given classical proof in such a way that we don't actually carry out these case distinctions and don't actually construct that maximal idea, but instead that we extract the positive information hidden in the classical proof. That's dynamical algebra. And this method of this informal technique of dynamical algebra is very powerful. For instance, it has been used to constructivize, so to give computational meaning to the proof of Serre's problem in algebraic geometry concerning vector bundles over affine space, over the affine space, telling us that all these vector bundles are trivial. You don't need to know much about algebraic geometry in order to appreciate the rest of the talk. And just saying that Serre's problem was very hard. Suslin earned the Fields Medal for solving that. And the proof was wildly unconstructive. That was not computational at all. But then Eason, a member of the constructive algebra community, came along and used the technique of dynamical algebra in order to extract the computational content of that. And nowadays, we also have a constructive proof of Serre's problem. Yeah, so the technique of dynamical algebra is very powerful and well established and very nice. However, again, there's an issue, namely the limitations of that technique are not so clear, because it's not so much a formal technique, rather it's an informal technique. It's telling you as a mathematician to reread the given classical proof in a certain way, and then try to come up with your new constructive proof. Yeah. And what Peter Schuster and I set out to do is to put this variant of dynamical algebra on a more formal basis, employing tools of constructive logic, of topos theory, of category theory. We wanted to actually have the maximal idea in some sense, so that the original proof simply applies, instead that the original proof has to be reinterpreted in some new sense. And that's how we did that. That's what I want to show you in the remaining 15 minutes of this time. Do you have any questions regarding the classical proof, the constructive proof, the technique of dynamical algebra? Questions like that?
Could you explain how this proof sketch results in the proof for the 2x1 case that you gave earlier?
Mm-hmm. Basically, it's just a matter of simplification. Yeah. So if we follow that template, we still have a proof which consists of parts. Yeah. It's not cases, but parts. Yeah. A first part where we establish that, and then a second part where we establish that. What you need to do at the end is you need to streamline the proof. You need to unroll intermediate definitions, get rid of insert computations directly at the places where they are used, like run the proof if the proof was a computer program, and then you obtain that computational proof in that specific case, this proof here. This is, by the way, something which you can actually do in a computer if you implement this proof here, the dynamical algebra proof, in a proof assistant like Acta. Yeah, because in Acta, you can not only have your proofs checked for correctness, you can also run your proofs. And if you run your proof, if you're as a computer program, then ACTA at the end will spit out this equation. Does that answer your question?
Yeah, thanks.
Yeah. Okay, good. So let's refine dynamical algebra. And we do that in 3 steps. And the first is, perhaps let's start with the second step. The second step is the following. So in order to come up with that maximal idea, use the construction of a maximal idea by Berardi and Valentini of 2004. So it turns out there is, in fact, an actual construction instead of an appeal to the transfinite in order to come up with a maximal idea. However, this construction only works if A is countable, if the ring is countable, which a general ring might not be. And even if the ring is countable, it might not be countable in an efficient manner, in a so that there might exist an enumeration of all the ring elements, and perhaps you can even write this down computationally, but perhaps it takes lots of computing power in order to actually come up with the enumeration. And also, you might just be in cases where there is no enumeration, and therefore we need a first step before that, namely enlarge the mathematical universe so that the ring A becomes countable. And this is something by Lovier and Tierney in 1984. I will comment on that in a second, yeah? And then the third step, if required, that depends on the given classical proof. If required, use the non-trivial continuation trick to upgrade the maximal idea. So we are now in the world of constructive mathematics, and here the maximal ideal constructed by Berardi and Valentini is in such a way that the quotient is a field in the sense that if an element is not invertible, then the element is 0. And some proofs require a stronger condition, namely that every element is invertible or is 0. Yeah? In constructive mathematics, this condition is stronger than the first one. And if required, we use an established trick in constructive mathematics called non-trivial continuation trick, or Friedman's trick, or A translation, or double negation translation, in order to upgrade a maximal ideal which only supports that condition into a maximal ideal which supports this one. Okay, so that's the general idea. Yeah, we enlarge the mathematical universe, then the ring is countable. Now, because the ring is countable, we can apply that construction by Berardi and Valentini, which only works in the countable case. If we and then we can apply the classical proof in that setting where we now actually have a maximal ideal. But all of these theorems are constructive. Hence, we can unwind all the required definitions from Topos theory and so on, and in the end obtain a purely concrete, effective proof, which specializes in that case of 2 rows, 1 column to exactly the proof I presented already. Okay, and I'd like to comment on, I think on the first two steps, and I think the first one might be more interesting to this audience, because the second step is more related to commutative algebra. But feel free, of course, to ask about any of the steps. So how does that work? And what do I mean by that? Yeah, what do I mean by mathematical universe? By mathematical universe, I mean topos. Yeah? So a category with certain properties, certain structure, rendering it especially nice. All of you, even if you're not topos theorists, know one topos, namely the so-called standard topos, which is the topos of sets. Topos of sets. But the topos of sets is not the only topos. In fact, there are lots of toposes. Yeah? And it turns out that you can do mathematics in every topos, not only in the standard topos. And more specifically, more to the point regarding this first step is the following. It turns out that, given a set, which might be uncountable, there's an enlargement of the standard topos in which that given set we started with now becomes countable. So we have the standard topos and a larger topos. We have an embedding from the standard topos to the larger topos, which we can use to import every object of the standard topos into that larger topos. And it now turns out that, this specific set we started with under the embedding now becomes a countable set. So in that larger topos, in that larger mathematical universe, we do have a surjection from the natural numbers to that very specific set we are interested in, called the generic surjection. In a suitably enlarged topos, there is the generic surjection from the naturals to the ring A we are interested in. There are lots of toposes. Sometimes toposes in which very weird non-classical axioms hold. For instance, there are toposes in which every function from the reals to the reals is continuous. Or there are toposes in which every function from the real to the real is computable. Or there's a topos. Yeah.
Excuse me, Ingo, I have a question. Maybe I'm not expert on these things, so I'm just
go ahead.
Forgive me, but you do you have actually a generic surjection to any object of this smaller thing?
No,
this means or not?
No. You first.
So what do you mean with generic? What do you mean?
Yeah, I will explain in which sense generic. But also to answer directly the question you asked, you need to decide which set you want to become countable. For instance, you want your favorite ring to become countable, or or perhaps you have some other set which you want to become countable. And then for that specific uncountable set, which you want to become countable, there's a custom tailored topos in which that specific set is now countable. However, other sets might still be uncountable. Yeah. So, for instance, if I force the set of reals to become countable, okay, then the set of binary sequences is still uncountable. It's very custom tailored to a specific set you start with. And what the generic surjection actually is, I will tell in 2 minutes. Okay. So there are lots of toposes. Yeah. some of them also very weird. But this specific topos, which you need here, so that you find the generic surjection from N to A, has the very pleasant property that it's closely related to the base topos. Namely, in the following sense, a first order statement holds in the enlarged topos if and only if it holds in the base topos, in the standard universe. Yeah. What's a first order statement and what's a higher order statement? To contrast that word, a first order statement is a statement which only refers to elements. For instance, the statement that that a matrix is surjective only refers to elements of the ring, or the statement that 1 equals 0 is a first order statement. The prototypical example of a higher order statement would be the statement that there's a maximal ideal, because this refers to subsets. This states that this is a certain subset with certain properties. But regarding first order statements, there is no difference between the enlarged topos and the base topos. Yeah. So if you want to verify that a certain first order statement holds in the base topos, you can just as well verify that this first order statement holds in the enlarged topos. But in the enlarged topos, you have that generic surjection available. In that enlarged topos, your favorite ring or your favorite set is countable. And hence you can apply tools which normally only apply to the countable setting, now only to your favorite ring, which in the base, from the point of view of the base topos, does not look like a countable ring.
Ingo, is this the same of saying that the inclusion of the smaller topos in the bigger one is logical?
Almost. Logical is a little bit stronger because logical also means that it preserves higher order logic.
Yes.
And this inclusion also only preserves first order logic.
And do we have a name for this kind of inclusions?
Yeah, these are open.
No, that's true. Yeah. Sorry, I apologize. Of course.
Yeah, no worries. So to be more precise, for those of you who do happen to know toposes, the topos in question, the enlarged topos, is the classifying topos of enumerations from N to A, and the geometric morphism to the standard topos, to a set, is open and surjective. Yeah. And this is what allows this flexible passage from the base topos to the large topos and back again. So regarding higher order statements, there's of course a crucial difference between the enlarged topos and the base topos, because in the large topos, the ring is countable, while in the base topos, it's not. But regarding first order statements, there's no difference. Yeah, and this tension is exactly what this techniques, allows this technique to work. Okay, there was the question, what is that generic surjection? Especially perhaps in dramatic cases, like if A is the set of reals, which we all now know to be uncountable. What's its generic surjection? Let me explain that as the final thing of this talk. So of course there is no surjection in the base topos from the naturals to the reals. Yeah, I think we can all agree on that. The reals are uncountable, no questions. However, there are lots of partial approximations to a surjection from the naturals to the reals. For instance, here's a partial approximation to surjection from N to the reals. This maps 0 to let's say a pi, yeah. pi, and it maps 1 to, let's say, 42, and all the others are undefined. Yeah, that's a partial approximation to a surjection from N to R. Yeah, it's not defined everywhere, and it also does not have every real number in its image, but at least it has those two real numbers in its image, pi and 42. And what this topos business with that enlarged topos and the generic surjection at the end of the day amounts to, if you unroll all the definitions, is the following, namely, that in the beginning of the proof, you start out with the trivial partial approximation, which is nowhere defined, like that. And then, in case the proof requires that a certain element is in the image of the surjection, perhaps pi, yeah, then you change your partial approximation. You make it better by saying, okay, well, then f of 0 is pi. And then your proof continues for a while. And then, again, it hits a stumbling block, because now your proof requires that 42 is contained in the image of the surjection. But then you say, don't worry, let me change the partial approximation again. Now it's 40, to this one. And then then the proof runs its course again, and perhaps you need to construct better and better partial approximations for a couple of times. But at some point, the proof will also have ended, will have completed its course. And then you are done. So at the end, this topos machinery to build this enlarged topos in which you have a surjection from N to your favorite set is not magic, but just bureaucracy, just dealing with partial approximations behind the scenes. Yeah? And each time where the proof would run into problems because a partial approximation to a surjection is not yet an actual surjection, we just fix the partial approximation specifically at that point which the proof requires. And then we let the proof continue. In case you are you like computer science language, this amounts to not running your program in the identity monad, but instead running it in a version of the state monad, which is sufficiently capable of progressing from not so good partial approximations to better partial approximations. What topos theory brings you here is the formal knowledge that you will be able to interpret all your classical proofs in that topos theoretic setting, in that setting of the enlarged topos, because you know from topos theory that any topos supports mathematical reasoning. Yeah, so you don't need to live in fear whether that technique of partial approximations might sometimes stop working for a specific proof. Instead, you know, well, a topos supports mathematical reasoning, therefore this will always work.
So,
okay. Yeah.
No, I was asking if you are finished or.
Say it again, please.
I was asking if you are finished.
Yes.
Or,
Yeah.
So that I can open to the audience and ask if there are questions to your.
Yes. Yeah, I would like to.
Okay, so thank you very much. That was really interesting, and there is time for some questions. So if anyone from the audience would like to ask.
I have a comment and a question.
Go ahead.
First, the comment, steps 1 and 3 in your outline, where you join a generic enumeration of A,
Yeah.
and 3 where you pass to the double negation subtopos to get
Right.
Boolean to work.
Yes.
The combination of those two is exactly what happens in set theory when you collapse the cardinality of A. The reason I mention it particularly is that although you cited Lovere and Tierney 1984 for the first part of that, the combination actually goes back to Levy, probably about 1964, 65. Now, the question, suppose I want, what does the following have to do, if anything, with dynamical algebra? So the following is what I would try to do if I knew the traditional maximal ideal proof of this theorem and wanted to get something constructive out of it.
Yes.
I would start with my ring A.
Yeah.
Sort of wish that it was a field and start doing the proof for fields. And of course, I would get stuck somewhere in the matrix. There's likely to be an element that's neither 0 nor invertible, so I'm in trouble. Oh, well, I have to, I guess I was wrong about this thing being a field.
Yeah, right.
I have to pass to a quotient to make that element 0 or invertible. So I make a little ideal, still nowhere near maximal, I suppose.
Yeah.
But to take care of that one element. And then I do my matrix and continue with the classical. And I have to do it again later. Some other element needs to be made 0 or invertible. So I said, well, that ideal I divided by wasn't maximal yet. I have to make it larger. And I keep sort of pretending that I have a maximal matrix tells me, no, you messed up. You don't have a maximal ideal. You have to put in more stuff.
Yeah.
I may never get to a maximal ideal.
Yeah.
I will get through the matrix. The matrix is finite.
Yeah, right. Yes. Yeah. Yeah.
And when I'm done, it doesn't matter that I don't have this maximal ideal. I've got the matrix working just like in the classical proof over a field.
Yeah.
So this is sort of a way to say, I don't need Zorn's lemma to give me a maximal ideal. I'll build it myself. And if I don't make it, that's okay as long as I get to the end of the proof.
Right, exactly.
That's a legitimate way of doing this. And is it essentially the same as the dynamic algebra, or is it essentially different?
Yeah, yes and yes. So first, yes, it's a totally legitimate way of doing that. Secondly, it's exactly what the idea of dynamical algebra proposes. Yeah. So like on your own, you just reinvented dynamical algebra. Congratulations. And thirdly, it's also exactly what that reified dynamical algebra boils down to when you unwind everything, when you unwind all the definitions. So this business with the generic surjection in that enlarged topos and so on boils down at the end to exactly what you just described. It's just like that this topotheoretic point of view gives you a more general way how to think about that. Yeah, like you right now were very specific to that example, having a look at the matrix elements and so on, and constructing that approximation hand step by step. Yeah. Instead, what the topotheoretic point of view gives you is it allows you to pretend that all of those things are finished. Yeah. It supplies you with a mathematical universe in which the ring is already countable. And then you can just apply that construction by Berardi and Valentini in order to just obtain a maximal ideal, which is then there and fixed, and it's just a maximal ideal, like you know it from classical commutative algebra. And then you can just write down your classical proof word for word. And if you unwind all the definitions, you obtain exactly what you just said. Yeah.
Okay, good. Thank you. That makes it very clear.
So,
Can I?
Yes, please.
So, Ingo, what you say, I think it's true, and I think it's very illuminating, but you're also selling us a dream in a way, because while it's true that at least in principle, this feels more general than what Andreas said, also not true, because I mean, this is not a general theorem. This is not something I can at the end of the day, this is a proof for precisely this theorem and precisely. So can we really make a general statement? Is this really a proof of this theorem, or we can really hope for something better?
No, yeah. So a message to take home from that, not concerning surjective matrices. A general message to take home from that is that you should appreciate those ideas from 1964/1965, or that reinterpretation of that ideas from 1984, to know that for every given set, which might or might not be countable, you have an enlarged topos in which it becomes countable, that you can then work inside that topos, and that all first order statements pass from that enlarged topos back to the base topos in which you are actually interested in. So if the theorem you want to prove happens to be a first order statement, you can just as well assume that the set which the theorem is about is countable. Yeah. So as long as you only want to verify a first order statement, your dream is valid. You may assume that it's countable. So like first order logic is not strong enough in order to find out that in fact that was just like a magical trick behind the scenes. And I think that this is useful in other branches of mathematics as well, because like sometimes you need the countability condition. And yeah, that topos, that enlarged topos gives you that. And also let me stress that it's only the form of the statement is important. So that has to be a first order statement. However, the proof may use higher order constructions as much as it would like to. Yeah. So you just need to very briefly have a look. Is my statement a first order statement? Ah, yes, it is. And then you know that you have the freedom to pass to that larger topos in which you have the generic surjection, and then work there.
So thank you, Ingo. I think our time is over, so I'm thanking all the speakers again, and I'll see you to the next installment of our seminar. Now,